Thanks for having me, everybody. So I'm Rob. I'm an industrial research fellow at the University of Sheffield. I've had quite an interesting career so far. Actually, I was at Manchester University, so it's actually quite nice to be back in Manchester. I was then in the military. I was a submariner. And then after I left the submarine service as a weapon engineer, I went into manufacturing. And I joined the MRC in the University in Sheffield in 2017. And since then, I've worked mainly in machining, so high value manufacturing and machining, and I'll come on to that. Over the past couple of years, I've had a really cool split role where I'm half a lecturer, teaching the students, doing PhD supervision, all the good stuff there. My other half of my role, I work with industry, so I work with companies such as Boeing, Rolls-Royce, McLaren, JLR, on both commercial projects, research projects, and for the capital, which I'm going to try and come on to as well. As we go through today. Now, I appreciate it's slightly different from all the other talks I've noticed on the YouTube thing. So I wrote this last year for my local sidebar in Macclesfield. So it's only been done once before. And I updated this weekend because in the space of a year, so much has changed. And I think with the pace of artificial intelligence and machine learning, it's so difficult to keep up. So hopefully you're going to learn something. And more than happy for questions. As I said, with my students, I have a no such thing as a stupid question rule. Okay, so please, ask away, and I'll do my best to answer it. If I can't answer it, I'll come back to you later and answer it with an email or something. Okay. Hopefully this will work. Okay, so the title was, and I wrote this last year, The Future of Manufacturing and the Fourth Industrial Revolution. When I wrote this, we were firmly going into this fourth industrial revolution, but as I stand here now, all that I hear in my career is all about the fifth industrial revolution. I just come from Cape Town to one of the most prestigious conferences on manufacturing systems, and the keynote was the fifth. So I'd update this title, and I'll come on to this a bit more about what that means. So I'm pretty sure most of you are familiar with the Industrial Revolution. So the first Industrial Revolution, we can think of Brunel, we can think of steam, 1700s, 1800s. As we progress through to the second Industrial Revolution, really thinking about Ford, thinking about mass production, and driven by the automobile industry. The third Industrial Revolution, 1970s, PLCs, programmable logic controllers, computers. That was the key thing here. Use of robotics, big production lines, automated, what you see on all the TV adverts, really. But this was it wasn't clever, it wasn't intelligence. Okay, you program something, you told the computer to do one thing, and it would do it. Okay, moving on to the fourth industrial revolution, which is where we're at now, really. Okay, so when we have these cyber physical systems, intelligence, it's autonomy. So it's how do we actually make machines do something, send something, adapt to it, react, really clever feedback systems as well. And I'm going to talk about just 4 or 5 of the technology, because there's so many of them, which is what we call the Industrial Revolution 4, or IR 4.0. And then I just added, this is where we're going next. So the fifth Industrial Revolution, what is it? Well, it's actually about having human in the loop. And so it's about how do we have technology, how do we have machines with the person and with artificial intelligence around that, for these safe, resilient systems with a huge sustainability focus, which is everything we do now, has to be really. And I'll try and come on to that a little bit at the end. I'm not going to cover that today, because that's maybe next year's presentation. I'll come back. Okay. So it's a bit small, this writing, but I'll just go around. So some of the technologies that you're seeing for Industry 4.0, as we call it, autonomous robots, so autonomous cars, or, autonomous transportation within factories. Simulations is ginormous, so modeling, integrated systems, Internet of Things, I'm sure you've all heard of. Cybersecurity underpins absolutely every single thing that we do now. Again, it has to, and an industry is putting an awful lot of money behind this. Cloud computing, edge computing, and additive manufacturing. So a lot of people will see it 3D printing, and I will touch upon this today. This is the future. It is ginormous, okay? And the things that we can make now are incredible. Augmented reality, augmented reality and virtual reality are big tools. We start thinking a lot about how do we train the workforce of the future. Okay, so we've got an aging workforce, people are retiring with a lot of skills, and actually kind of people are coming through with less training, and it's things like augmented reality and able to kind of train those people faster. So we can look at something and it can give us instructions of how to do it, where to go, and this is where you're going to see a lot more later. Big data, I think everyone appreciates that we're in a world now where we're centralized every single thing. Is how do we make the most of that? And really, that whole bit about this digital transformation, it's all about connectivity and data. But we can appreciate we take data from everything, but it's how we use it. And it's one of the challenges that I see now with a lot of the big companies. They are getting the data, but half the time they're not doing anything useful with it. And that's kind of the problem we have to address, really. So what's the drivers? So I stole this slide from Professor Sam Turner he's the CTO of the Catapult Centre. And really, the driver is UK net zero. That's where everything is being driven from. Every single grant I apply for, every time I talk to a company, whether it be Rolls-Royce, all we're looking at is sustainability and net zero, and that drive to get there, in everything they do from product design through to manufacture. And here's some of the things that we're looking at. What we're driving: the aerospace industry, electric propulsion. This is happening. Okay, so especially for short journeys, we're looking at electric vehicles. As longer distances, we're looking at more hydrogen. Okay, sustainable aviation fuels. The next generation of jet engine is absolutely incredible. Take a look at kind of the turbofans or the ultrafans that's going to be happening. These new gearboxes they're making have to withstand such incredible high temperatures and forces. How do you manufacture them? It's actually really, really difficult. So one of the things that we're looking at is how do you manufacture that jet engine of the future? Because you're going to need new tools, new processes. Okay. Urban air mobility, air taxis. We will see this in our lifetime now. It's happening. It's no longer a pipe dream. Electric propulsion in electric vehicles, autonomous cars. In the marine world, we're going to start seeing zero-emission ships. And you're going to start seeing these ships that have got ginormous sails on them, and with hydrogen powered. The energy world is fascinating right now. There's a lot of push towards what we call the small modular reactors. So Rolls-Royce are digging heavy into this. Obviously, transitions to hydrogen, carbon capture units, offshore wind, and then also we're looking at things like the next generation aircraft, space, and then personalizing for pharma. That's now. That's what we're looking at, actually, the driver now. In between, the net zero target and what we are now, there's a whole lot of products that we haven't got a clue what we're going to manufacture. And we have to be parts and resilient to be able to make these quickly. So that's the driver for the UK manufacturing sector, the world manufacturing sector at the moment. So how do we kind of go about that a little bit? I want to see what I work for. So I work for the Catapult Centres through the AMRC. That's government funded. So it's driven by industrial strategies, if we have one, but it's ultimately driven by government. Okay. And that's a series of 7 centres. Okay. So we've got up in Scotland, the Advanced Forming Research Centre, Centre for Process Innovation, Warwick Manufacturing Group, MTC for Manufacturing Technology Centre, Composite Centre, my world, the AMRC, and the nuclear MRC. They're spread out all over the place. And we're complementary, we're not competitive. So we have a national strategy, we have national working groups, and we all work very closely to address all the challenges. Maybe the productivity challenge is a big one, and without trying to kind of step on each other's toes and help. Obviously, there's some good overlap things, but where we can share best practice. And so I sit on the Sheffield side. This is what the Sheffield site used to look like. So hopefully, you might not realise, but this is where the Battle of Orgreave was. So Sheffield, famous for our steel industry. And 20 years ago, or 22 years ago, Professor Keith Ridgway, he had the idea that actually we're not getting research out of academia. It's not going to industry. So we have this thing called technology readiness levels, TRL 1 to 9. So 1 is get academic, lucid thinking research. Number 9 is on the production line. It's been worked. It's progressed through. We realise this 4 to 7 category, we call it the valley of death. Okay, research is stopping; it's not going there. So how do we address that? And what he wanted to do was create a set of sensors, or create a sensor to start off with that would address this. So on the basis of here, we then have this now. This is the same picture, the same one. So just in the middle, this small building here was the first building. So it was an absolute greenfield site. You couldn't see anything. Started off as one. And slowly over time, we built the centres up. And over 20 years, it looks a bit like here now. But because of what we have now, so we have the Welding Institute, we have our nuclear MRC here. This is Rolls-Royce. McLaren is just up the way. And if you can see the zigzag building at the back of the middle, okay, because of what the MRC had developed, that was Boeing's first ever production facility outside of the US. So it's great. So it's on the doorstep. So I'm here weekly, just popping up, seeing how they're doing, solving their problems. And now we have this phenomenal hub of advanced manufacturing research based at Sheffield. And other centres are now kind of following the same model that we do. So technology themes, what kind of things do we do in my centre? So subtractive manufacturing, this is my bread and butter. And I would love to give you a whole hour on that, but I'm pretty sure you're bored within the first 10 minutes, okay? But when I say subtractive, you know, I manufacture things like airfoils, turbine blades, compressors, wing spars for jet engines. So really advanced, hard to manufacture, hard metals, and some aluminium obviously as well for the aircraft structures. Smart manufacturing, I'm going to come onto this today. Digital twins as well. Artificial intelligence, I'll briefly touch on this. Additive, robotic, I do a lot of work in this. And now we're looking at things like near-net manufacturing. So sustainability is like a driver. So if we can create a product that's roughly nearly the shape we want and machine away only 10% of it, as opposed to machining away 80% of it, you know, we're now starting to kind of, reclaim our carbon, we're starting to have less energy. So this is a huge bit. With 3D printing, we can start making more near-net shapes as well. But it comes with its challenges. Is it just as strong? Machining. Because we've got additive as well. So it's now the term that we use. So subtractive is where we're having some bulk material and we'll machine it away using CNC machine tools. Okay, and then that'll leave us with the shape that we want, our desired part. As opposed to additive, where we'll start off with maybe nothing, and we're going to build it up to the shape that we want. Okay, so it's two sides of the coin. It's quite a newish term in the last 5-6 years. I think people are starting to refer more to things like that. That is machining. That is machining. But it's just a bit more technical in terms as well. And likewise, we can have metallic subtractive processes, non-metallic subtractive processes. So, for example, if we're doing composites, like we're doing an awful lot of machine composites these days, which is very, very difficult. It's actually carbon fibers and things like that, and your layups and stuff, as opposed to stone metals. Good. Big data, work on a lot of this. Composites, like I just mentioned, composites is a phenomenal world, and we'll see a lot more of this now. Lightweighting. So how can we, build these products from layup carbon fiber and different things? And it's a mixture between engineering and some kind of phenomenal tapestry. It is just incredible and incredibly strong, but very hard to work with, and they wreck your tools. So it's a really difficult thing. But if you think about your F1, your McLarens, your all these kind of fast cars, but now we're going to start making things like fuel tanks for jet engines, different kind of storage mechanisms for hydrogen. So it's got a lot of space within this. Starting to look at 5G control and communications within factories. Lots of sustainable manufacturing have come out, and then zero defect manufacturing. Zero defect manufacturing is what we're really trying to achieve in this world, where we're making the product right the first time. And so ultimately, if we can do all sorts of virtual testing, so rather than do it on actual physical testing, hopefully before we even get there, it's not an iterative process. We make that product right the first time. Therefore, we have less waste, less scrap, and it's cheaper ultimately, but it's more sustainable, which is what all this fits into really. And on the right-hand side, you can see some applications which was similar to the drivers, future propulsion, lightweighting, electric vehicles, defence, medical, some really fascinating medical. I've got a bit to show you on that later. And then supply chain and green hydrogen, we do a lot of work on. So there's about 600 of us in this facility. And that's everything from the experienced operator all the way through to our project engineers, PhD to the top as well, and then out to the applications teams. Good. Any questions before I continue?
Just a little question. In your application,
yeah,
they're all strongly
yeah. Funny you should say that. I think next week there's a conference that they're hosting, which is on food production. I'm not familiar because it's actually kind of we've got an AMRC in Wales, which is co-hosted with Airbus down at Broughton, and they're really pushing with the food production down there as well. So it's a big area. I think next week, there's a big conference on that we're hosting. So, yeah.
You're mentioning.
Yeah. I mean, we seem to be doing more and more every year, with these centres. So, I'll stick to my subtractive, which is good.
Wait, mate, are you okay just to repeat the question again for the next one?
Yeah, sorry, yeah.
No worries.
No problem. Okay, so I've got some technologies and some case studies that either I've been involved with or that some colleagues of mine have been involved with as well, just to add a bit of context to it. So here's a definition of smart manufacturing, and I've taken this from the American Institute of Standards and Technology. So it says that smart manufacturing systems are fully integrated, collaborative manufacturing systems that respond in real time to meet changing demands and conditions in the factory, in the supply network, and customer needs. Okay, a bit of a mouthful. My interpretation really of smart manufacturing is when an industry or a business will take data and they'll use it to make better business decisions. That's really the crux of it for me. Okay, a lot of factories, they are taking data. They have them for years. Quite a lot of them have just taken data, pen and paper, and I would say probably 90% of companies are still using pen and paper for most of their data collection, I would say, but it's about how do we use that information properly and how do we make better decisions, more profitability and better on production as well. So here's a bit of a case study. Back in 2017, 2018, we did a catapult funded project. And so some friends of mine, what they were looking at was just taking data from machine tools. Okay, so CNC machine tools. Now, actually, what they realized was all these machine tools got different controllers, so different proprietary. Some of them were black box. Some of them you can access the data, some of them you can't. Some of them can talk to each other. Now they're charging a fortune for accessing this data as well. And so actually, it was very difficult. What they decided was, can they build something even more simple? What they did was they just took a Hall sensor, okay, which is here. So a Hall sensor is going to measure your currents, okay? And they were able to clip this on the back of the spindle, the wire behind it, but not accessing the machine itself, not going inside the computer. And now they can determine, is that spindle on or off? Simple as that, okay? So now they can develop an app, and they can have an edge device, so just a Wi-Fi box ultimately. And now they can go and send this to the app and say, is your machine tool, making chips? Is it cutting swarf? And that was as simple as it was. And they decided from that to spin it out, and they started this company, Forjo Analytics. And so what you get is something which looks a little bit like this. So you can get just a dashboard, which quite a lot of factories are taking on now. You can just zoom it in a bit. Take this as an example. So here's the Haas milling machine, and you can just see, is it on or is it off? But finally, this company, whoever's using this, you can start making business decisions, figuring out why is it happening, what's happening. Is it to do with, shift changes? I know of companies that realise that actually it takes 45 minutes to warm the machine tool up or to get it on. So actually the previous shift would then start warming it up rather than wait till this shift to come on. Okay, and really, really simple things. And now all of a sudden, this is smart manufacturing, and you can start making really good business decisions through this. And a lot of companies have started using this now. So here's a small case study. So a Sheffield-based company, Durham Duplex, so they make industrial blades, industrial knives, and they took this up. So their problem was they were taking data, it was all by hand, they couldn't quite figure out, where the production problems was happening. So we started off with one single grinding machine, and on one single grinding machine, they were getting bottlenecks, and they had plenty of demand, but they couldn't supply, but they couldn't figure out what was going on. And manual, inaccurate data, no benchmarking whatsoever. And all they did was they installed this system, figured out what was going wrong, and then they boosted productivity from 5 products a day to 25 a day, which is 400% increase in productivity, just because they can analyze it properly, because they were not taking data manually. And now they can make decisions. So they rolled it out on one machine, and then now they've got it on 10 machines. So they start off simple, prove the concept, and now they get confidence, and now they can kind of go to further. So it's a fantastic example of smart manufacturing with something incredibly simple. Now, there are far more advanced smart manufacturing methods out there. This is a really kind of neat, simple one to demonstrate with. Okay. Digital twins. You've probably heard a lot about digital twins. I imagine they're everywhere now. It seems like everyone's got a digital twin. And there's lots of different definitions of them, okay, depending on who you talk to and what. So this is from IBM. They were quite early onto the scene with digital twins, and they say that it's a virtual representation of an object or system, spans its life cycle, updated from real-time data, uses simulation, machine learning, and reasoning to help decision making. I don't think it needs all that, to be honest. Okay, I think from my definition, if you have some physical asset or something, a physical process, and you have some computer model or something, and they're connected, okay, and they're communicating. And so you have to have the physical and you have to have the computer. If you just have a computer simulation, that's just a model for me, okay? But actually what you can now do is try and link the two together and start doing things. And there's a mixture of, the time scales. It could be real time. Is real time, does that mean every thousand hertz? Or does that mean 1 millisecond? Or does that mean every second or every hour? Or, what we're going to have on it? So I've done quite a bit of work on this. Here's a little project that we did in collaboration with the control department. What you're seeing here in this video, this is a little small, what we call Festo kit. Okay. Now, within here, I'll just pause it actually before we go back. Within this, what you're seeing is the exact same equipment that you have in a normal factory. Okay, these are Siemens PLCs, grammar logic controllers. They've got RFID, so radio frequency ID tags on them, and conveyor belts. And so if you had a big factory, okay, which has got products going around, it's just a very small version using the exact same equipment. Okay, but we can play with this and do things to it. Now, we can link that up and we can do a model of this. So this is a 3D discrete event simulation model. All this really is a CAD model, okay, overlaid with a discrete simulation model, which is relatively simple, okay? And this is the process. And this process is actually putting a phone case together. The one case goes round, it measures it, it brings it, stamps it, a bit of pneumatics in there. Now, within this process, I'll just try and stop it here as it goes round. What we can see is as it goes round, these little symbols, circles, they'll turn to green. Now, what that is that it's recording the RFID, the radio frequency ID tag, when it goes over it, okay? So that can then update live systems. It can know where the process is. But actually, what happens if you've got really big production lines? Okay, so you're only measuring this kind of things at discrete points. So what we did was, hopefully the next bit will come up. We decided to link it in real time. So now what we decided to do was, behind all this, we put a set of series of cameras, really simple cameras. Now what we can do, we can have a look at where it is. We can do some vision detection. okay, using open source computer vision. We can do a bit of machine learning to predict and recognize where it is. And now what I can do is I can send that data in real time, okay, through something called OPC UA, which is a connection. And now I can actually know exactly where I am, okay, without having to wait for it to reach these stations. And so this is a lovely example of a digital twin. I've got, a physical system, a computer model, and now it's been updated in real time, through a computer vision system. So I know exactly where it is. I'm not having to wait for these RFID stations. And it's a wonderful digital twin. And you can do many different things with these. I mean, one option, you can update your models. So actually, how accurate is my timings? And you can feed that offline, and you do lots of offline optimization. I might have a factory, with multiple different routes going around, and I could start saying, actually, now I know exactly how long this takes. I could all of a sudden just say, okay, well, now let's say this station's broken, or it's down for maintenance. I can quickly do some simulations offline. I can run 1,000 simulations in 5 minutes and tell you what's the next best route to do without even going onto the shop floor. So this is where it comes into its own. When Boeing brought their factory to the AMRC or to Sheffield, this is the exact same software that we used to design their layout on the factory floor. So exactly one, which is lovely. Now, this was a great project that I worked on, and I was amazed that they let me do it, actually. So this is the EchoSpeed machine tool. It's a beast. If you look, you have to walk up through here, and I've included a picture of my friend Chow inside it, so you've got an idea of kind of how big it is. So this will manufacture your wing spars on your A350 and the wide body, and it will cut through metal like butter. It's incredible. Okay, so with this project, what I wanted to do was wanted to get real-time data from the NC controller. So I wanted to know the position of where this spindle was at any point. Okay, feed that into my model. In my model, I had some very complex simulations that were able to estimate, okay, what material has been removed at any one point. Okay, based on that, without having to put expensive sensors into the machine tool. So the sensors that will normally sensors that will be able to predict or measure cutting forces, they're around about 60 to 80,000 pounds. Okay, and they're quite sensitive. If I'm going to put them in a machine, that's going to be covered in coolant, covered in swarf, really high kind of forces. I'm going to break it pretty quickly. So you don't want to do that. So what we did, you look here. So I was able to take data live, put it through a system, and use an online cutting force simulation. So I was able to predict, okay, what was happening without having to have a sensor in there. Now, obviously, I did have a sensor when I was validating this to make sure it was accurate. Okay, and I was able to do a couple of different things. The one was I did chatter detection. Now, chatter is when your machine goes into resonance. Okay, so you hit that natural frequency, and all of a sudden your cutting forces will spike, and you'll probably break the tool. Now, if you break the tool, you might have a workpiece that's going to be 60 to 100,000 pounds if you spent this amount of time doing it. So you're either going to have to rework it if possible, or scrap it, and probably get your job scrapped as well. But the beauty of this is we're able to predict that it's about to hit resonance and change our spindle speed before it even happens. Now, existing methods, if you're, for example, just taking the power signal, you have to actually kind of go into that mode and risk damage before you can then detect it and come back. And we were able to look ahead and say, actually, it's going to happen. Let's change it. And that worked really nicely, actually. Similarly, we did it for adaptive control, where I knew that I was going to go into some really big, big cut, for example. I could back off and slow down and, balance them forces. And then we also applied it to something called machine-induced residual stress. So this was pretty impressive, where if you've got a really big part and you're machining lots of material away, well, what's going to happen is you're going to put a lot of residual stresses in that, and that's going to cause distortion. When you take it off the machine, what you thought was accurate, now the part's gone like this. And I know we might be talking millimeters, but that's ginormous in my world, and all of a sudden you're out to it. You're either going to have to do some remachining, put it back on, more inspections, more testing, and that all costs money and increasing things as well. We're able to predict the distortion in advance, and we changed our strategy online and prevented that happening as well, all through the digital twin. I've got a bit of an example here. So Productive Machines, the spin out that we spun out after this project. And here's a demonstration. And what you're seeing here, okay, is the same machine. You're seeing the simulation and you're seeing the measured values as well. The top right, you can see kind of the engagement tool as it's going through. And this is spine active machining, and you can see it goes on there. And we're not far off accuracy as well with this. So live data, I'll play that again. So you're seeing, live data going into our simulations, updating in real time, and we now have a digital twin of what the process is here. And we can use this for all sorts of different things now, which is what we're doing. But ultimately, we're saving ourselves a very expensive bit of equipment. We published this work, and we got nominated for the National Engineering Manufacturing Awards for innovation. So I was pretty pleased with this. Any questions on digital twins before I go to the next?
Trying to make sure that
Yes.
is there.
So there's various things. Obviously, a lot of this comes with a set of uncertainty bounds. So within our modelling, we've got a set of assumptions, and so there is an uncertainty. When it comes to things like kinematics, so how fast is my tool and what position is my tool in? They're exact. Because that's going through, and I'm feeding that exact data into my model, which is fantastic. Okay, things like other functions of it, the cutter engagements, the effects of coolants and things like that. We have some complex models, and obviously that's what we don't know. This one here was purely analytical, which by that I mean there was no machine learning within that at all. So now I think the next step, which we have done some research on, is combining both the machine learning with the analytical models to try and update and minimize some of this uncertainty. But it will propagate through. It has to. It's very complex. Yeah, for sure. Questions.
Your examples are very interesting.
Yes. So the question was about, this was applied to discrete manufacturing. Is it being applied to process technologies? Yes, it is for sure. So we've got a rig at the Diamond plant called a pilot plant, and it's a student plant, and we can manufacture, pills and things like that. And our students in my department this year and last year, they made a full digital twin of the process, and fully sensorized production units. And they're doing digital twins of the process already, which is great. So yeah, yeah, it's good. I mean, it's a bit out of my field, but it's happening. I think but once you see it here, digital twin, you'll see it everywhere. Everyone is jumping on board the digital twin bandwagon, and yeah, it's not just manufacturing; it's everything production wise.
It's sort of determined part of the break. So you get a nice part, and then you face the cortex and it breaks.
Yeah, so the question was about kind of, can digital twinning help determine if a part's going to break? Yeah, absolutely. So I think there's a couple of different things. So one, in my world, it's about you having so much data, and in the digital twin of the part, is it going to meet conformance or non-conformance? And as we go through this production line, can we use the data we have to minimize the inspections, which will then, reduce the time to market, increase productivity, and save money, which is great, which is yes. Now, also, going back to yours for other things, I've got a lot of colleagues that work in structural health monitoring, and they do an awful lot of work in digital twins of wind turbines. Now, this is where it's really coming into its own, because actually you can now start having digital twins of wind turbines, all the way at sea, and you can start predicting when they either need maintenance or whether they need to go offline and things as well. So yeah, absolutely, definitely going to happen. We do it a lot of toolware as well. There's huge amount of research on toolware at the moment. I stay away from it. It's very saturated. But if you can predict, when that tool life's going to happen, actually and push that a bit further, save yourself some money, less changeovers, things like that, and it's a really big win. So yeah, it's cool. Okay, so machine learning and AI, it's everywhere. It's ubiquitous these days, and I find kind of just working in the field and teaching in the control system department that I have a job to keep up with it, on a yearly basis. I took this from ChatGPT. I hope a lot of you kind of understand, if you use ChatGPT here. I've now got my parents using it for everything, even like Christmas cards and little things. But I asked ChatGPT what was AI, and it came out with this one. It's a subset of AI, developing algorithms and models that enables computers to learn, make predictions or decisions based on data without being explicitly programmed to do so. So for me, I'm a systems engineer, really. When I look at things, I see a system has got an input, it's got an output, okay? And there's a process in the middle. Now, and usually there's some kind of feedback, okay? That's the world that I tend to work in. That's been around for many, many years. And the tools to figure out, how do we control a system, there's been around for so long, hundreds of years, okay? We have these classical methods that we call them, system identification. Now, if we know the input, we know an output, hopefully we can figure out what's going on in the middle. So then if we have this model that we can figure out what's going on in the middle, we can set a new input, put it into our model, and we get a new output. That's really all machine learning is. Okay, so if we've got a lot of input data and output data, we can figure out what's going on in the middle. And there's a lot of complexity. Now, it's not the be all and end all, because actually, quite often you miss what's going on in the middle. So you miss that kind of the fundamental physics, the dynamics, what's going on. It can help infer an awful lot of stuff, but nothing beats, some of the classical methods as well that might infer and be fully transparent about what's going on. But I put a couple of case studies together. I put this one in purely because I did it before Christmas, and it's just a really interesting little project that I did. So obviously I'm in machining. This was me on a 5-axis machine tool about to machine a knee joint. Okay, so we've gone from aerospace to medical now. The only reason I'm showing you this is just to show how complex the motions can be in 5-axis machining. Okay. So here's a couple of videos that I took. And you can see, I've got the C-axis here going crazy, going round. The B-axis is coming up. I've got kind of a really complex non-linear motion. I'll show them again because I really like them. But predicting this behavior, okay, obviously we can predict the accuracy of it, but, we know what it is, the model. But how long that's going to take? A planner, okay, in the office has no clue how long this will take. The traditional CAD engineer, the CAM engineer, could not tell you, okay? Because you'll put your feed rate in, that's how fast your tool's going, okay? But actually, because of your tolerances, depending on how fast you're machining, or could be 10 microns, 50 microns, 100 microns, okay? The difference can be 100% in your cycle time. Now, this is massive. So my PhD was actually kind of developing methods to predict this behavior. And I remember I was really cared about how fast that tool was moving through it, because then it could predict the forces. And I presented this to the tech fellows. No one cared about that. All they cared about was the cycle time. Okay, because then all of a sudden, the business planners can figure out how much it's going to do. They can do accurate costings. And that's all they cared about in the planning. And I'm commercializing this software at the moment, on the basis of just this accurate planning and cycle times. Now, what we did was here, we took a set of input data, which is what you're seeing here on the left-hand side. So I can take my G code, which is kind of what I command in my machine. So I take feed rates, I take how long this tool goes to here, lots of other different kind of geometries. And I just record one single thing for this. All I did was record how long it took. I can do it for either every discrete line on the command or one single one. And this is the model in the middle. Looks a bit crazy, but really, it's not. Just feed it in there, feed my data, input and output. And now every single other time I go to create a new one, I can now predict within 2-3% error, okay, how long it's going to take. Whereas previously, for this particular example, it's about 22% error all the time. Other examples I've got, especially in the roughing when I'm taking machining wing spars, I was getting 100% errors. So pretty impressive.
About the machine learning side of it.
Yeah.
You've not developed your own neural network, so what do you use for that side of it, or are you not allowed to tell us
No. So with this one here, this is called bidirectional long short-term memory. So bi-LSTMs. I've done projects and published papers when I've used neural networks and different kinds. And choosing the model structure, it's part of the battle, and it's a bit of an art these days. Kind of to choose it. The reason I chose this one because it's really good at sequences. So actually, kind of this method in particular, I know that what happened before is going to affect what happens afterwards because of kinematics. It has to speed up and slow down. Therefore, this was great for sequences. Things like a lot of normal networks are not good for sequences because they're taking everything as discrete. And so it all depends on the application.
So I suppose you go back even further than that then. So can you just buy these things as models that you put on in your own computational thing, or do you rent someone else's computing mics to do this?
Yeah. So the question was asked about how do you use existing technologies, existing tools. So there's various software you might have heard of. Languages like Python is a very popular one. MATLAB is one that I tend to use quite an awful lot. Now within them, there are a set of packages that are all pre-built that you can just go in, put your inputs, put your outputs, tune it, and then run it. So it could take anything from an hour to train this to 10 hours, depending on how much data that you've got. But yeah, there's this now. Yes, yeah, and depending on the scale of the problem. When I did this, I had about 20 hours of training data, perhaps. So I could run this on this laptop. This laptop's a decent one. Otherwise, I could put it on a GPU somewhere and pay for it, to some, big mainframe computer for some time, more complex calculations. Yeah.
It's reachable to most people.
Everybody, yeah, and not only that, you can go and if I wanted to, I could just go on to use a normal laptop and then just send it off to the cloud somewhere, and then use cloud-based kind of computing to do it for me if I wanted to. Yeah.
Initially, how many parameters cover the model have you select? And what do you get measured?
Yeah, good question. So, question is, how do I do parameter selection? I originally developed a method that was purely analytical. Okay, so I developed a brand new interpolation method of CNC motion control. And because I'd done that, I knew personally just what the impact was of each of the parameters. So then we had to play around. This is actually my PhD student that developed this one. And we started off with a handful of parameters. We can do what's called a sensitivity analysis and see what the impact is, and then narrow it down. Quite often it's a bit of guesswork, start depending. But with this one, we had the deep domain knowledge to be able to apply for that as well. Yeah, it was a good project. I think for this one we had about 8 to 9, and the only time we added some extra ones, the sign A and the sign B at the bottom. We started looking at what we call singularity. When a 5-axis machine tool goes near the singularity point, it can spin around really quickly. Okay, and that can cause a lot of issues. And so this was a nice easy way of included that variable within that. So that was the only addition really that we had on this one. Cool. Yeah. So the next one, I just want to show another example. And the reason I put this one is just to show it's not all about just lots of data in terms of time series, as I call it, sequential data. Within this one, this was my friend Javier and James and John. What they did was the same machine actually I just showed you. They were able to apply machine learning methods and to defect detection on CNC machining. So what you're seeing here is a process on the left of machining, and then on the right is a series of spectrographs. Okay, spectrogram, sorry. So the spectrogram, on the x-axis, what you're seeing is time, and the y-axis is frequency. So now, as we go through a process, we can listen to, or measure these frequency changes and start looking at it. So when we put this through machine learning network, we're actually putting the image through. And so that's what it's looking at as a whole. And so through that one single image, we can start training the data and use these images to detect things such as misalignment, bores, tool wear, based upon this single baseline. Now, this project was done actually a few years ago now. This is 2019, I think. And this is what we called supervised machine learning. So that's when you've got an existing set of data. So you say, this is good, this is bad, and you train on these. So when you put something in now, it knows it can detect it. We've moved on a lot from this, and now we have something called unsupervised machine learning, which is where you can just put something straight through, a system and be able to detect it without having labeled the data already.
The sound as well.
So this is, so this, we have, what you're seeing here, if I remember correctly on this one, this is a dyno, so this is probably recording about 10 kilohertz, so vibration signals, but we also use acoustic emissions, which is more in the megahertz range. We use audio, so obviously much lower. So depending on what we're trying to do, it's all the same process. So it's all just, using the exact same frequency domain analyses or time series analyses for the same thing. So yeah.
I think this was very useful in medicine for detecting cancer. The images.
It's ginormous. It's ginormous. And actually, my boss in the control department, he's got so much research in doing that exact thing. So basically using these images to detect cancer and things as well. Yeah. So he specializes in machine learning. I haven't got the figures, but I mean, I know now, I think a lot of radiologists, they're using this kind of technology just to speed up the process. And then, because you can get through so many, within a single kind of day, and then they can go and double check and then use it. So exactly. But not only that, the beauty of the machine learning is that it's detecting patterns that you cannot normally see because they're so complex. And you can change, you can do many different mathematical computations to these, change them in different formats. You can find underlying patterns and things that we wouldn't be able to see. Yeah, exactly. For a friend of mine, she's currently working on supporting stroke rehabilitation, and she developed a machine learning method, so it can support people with stroke rehabilitation, which is great. But that's through electrocardiograms in the head. So cool. Okay, additive manufacturing. I just put a couple of slides in here just to show the benefits really of 3D printing. So additive uses data computer aided design, software, 3D object scanners to direct hardware to deposit metal layer upon layer in precise geometric shapes. There's many different ways of 3D printing, but really what I wanted just to show you here was that 3D printing, when I think about it, it's metal. Okay, it's not plastics anymore, right? And this has been going on for quite many years. And you'll all have flown in planes now that have got parts that are 3D printed, believe it or not. Okay, and this has been going on probably about 5-6 years that's already happened. So GKN Aerospace, their 3D printing center is impressive. But the benefits are, you're able to take these components that are incredibly complex, and what might have taken 300 parts, you might be able to reduce it down to 10 parts because you can build the structures with it inside them. But if you can take 300 parts into 10, that setup time and that kind of putting things together, you just reduce it by 90% or whatever. So straight away you're saving money, I think. So this one, this is a casing for electric motor and for electric vehicles. Now this was a magnetics project. What they want to do is put a heat sink in there with some ducting. This is actually a CAD model. That's not real. Okay, so that's computer aided design. They'll design it offline. Then they're able to kind of simulate kind of the flow rates. Then they can design what the actual deposition is going to look like, which is what you're seeing here. And then finally, what you're seeing at the bottom end as well is the manufactured products in the end.
If we use the 10 parts, not use the failure, right?
Yes, yeah, definitely. Yeah, for sure. So the question was, am I reducing the failure rate? Probably as well. Now, obviously, because you're manufacturing things, building it, are we putting different stresses in there? Are we doing, the level of complexity in here is ginormous. And I've got a lot of respect for people in the 3D printing world, because you have to think about so much. I've actually done some work with them as well, where I related the CNC behavior to what they were doing, because actually it was controlled the same way. So it's quite nice. So there are parallels between my world and this world as well. And we even have machines now that will, in the same machine, it will layer the metal, and then it will go and CNC and machine it as well within the same. And we're seeing that's developing different kind of structural properties and making it stronger, because you're doing things straight away. So you can actually kind of build a structure as a whole without taking it off the machine and still CNC inside it, come off, build over it, all in one thing.
Material in that, or is it always just a single?
Good question, and I'm not quite sure. I have seen some bits where we use multiple materials, but I think for the moment, majority of it is probably kind of the same, but not my area. But yeah, I imagine it's quite complicated in terms of the machine setup as well in itself. Yeah. And so one more just example here to show you that this is end topology. Again, I just wanted to show you this because you can see how all of a sudden we can build these structures, with inside single, units, and all of a sudden this is cheap. Okay, back in the day, if you were thinking about that, you were to try and manufacture something like this. I mean, just the design stage alone. Now you can go to a computer, you can type in your CAD model, probably use some artificial intelligence to do it. Then it would send it to the machine, and then by lunchtime, you're going to have something that's built like this. And all of a sudden you can test and you can prototype. So in the world of prototyping and rapidly creating these new products, 3D printing is just incredible. You'll see a lot of, whether it be race teams or a lot of the bike race teams as well, especially cycling, they'll be doing things like this all the time. They can quickly change something, they can do some simulation and run it.
What sort of the metal that we used to, like stains or titanium, what materials that are used in this?
There's a massive range, to be honest. Yeah, a huge range. I mean, I've worked with some titaniums and things like that, and some nickel-based alloys. Some of the work I've looked at is actually about using this for making fan blades inside the jet engine as well, and things. So, yeah, it's a big range of materials. Okay, we're almost kind of getting through these technologies. So I wanted to show you robotic machining because I've done quite a bit of this in the past few years, and it's just very cool. So, when we have these really big CNC machine tools, like I showed you before, they're very expensive. The one I showed you previously, probably about 15 million or something, but we've got this ginormous area that we can do. So we can manufacture these wing spars of these jet aircraft. But actually, what if we get, a decent robot and we put a spindle on the end of it? What happens? So this is the Titan, which is a factory of the future. Now we can, change our tooling here. We can kind of manufacture, go, but we've got this huge operating envelope now where we can manufacture things. And this is what it's going to see in the future. Problem is, it's a flexible structure because it's a robot. Okay, so we have to overcome that. It's got its own issues with the dynamics, own issues with the kinematics, accuracy, because we've got this, even though it's got a huge end effector, we're probably getting a deflection here, I imagine, that's somewhere in the order of 0.5 millimeter. That doesn't sound a lot, massive in my world, okay? But actually for certain things, it's okay. So what about if I want to quickly manufacture loads of really big components, rough it out quickly, and then use a different machine to finish it later, or a different process, or I can use these for, for welding or whatever. Now, within this as well, what you're seeing is we can hook this up. So back to your smart manufacturing and your digital twins. And so you can see at the top, we've got a CAD model, and we can attach this in real time as well. So we can do some digital twinning with this technology, and we've done it with this robot. We've also linked this robot up to the bigger system. So all our machine tools are connected in the cloud across all of our sites, and we can access any machine tool at any time and the data. And so what you're going to see in a minute, okay, it's going to come up, and we're going to log in. So now I can go to the manager or whoever I want, Find my machine tool. There we go. Let's go to the UK. And it's all sensorized and it's all hooked up. And so this is another example of smart manufacturing. So now we're going to go find the Titan. We can click onto it, and then we can see, is it in operation? What jobs has it been doing? What's the utilization of it? Obviously, this is 2017, it's a bit old. And we can go and have a look at it. And it can be a little bit big brother, because I can see if the operator's been slowing down the feed rate or speeding up the feed rate, which some of them don't like. But then ideally, we can then figure out if there's problems, then solve that problem and, go back to the drawing board with stuff as well. And here you can see all linked together as well. But the future to this stuff, really, if you can envisage, a big factory, really long, with multiple, robotic machine tools in there, and I could put in a part, model at one end, and at the other end, it's going to come out this finished product. Okay, we call it the automated tool room. That's what we're going to. And
these are start agnostic.
Yeah, the bullet material at the end is going to produce it. And there's a company called Rodin Machining in the Netherlands that I had a meeting with just before Christmas, and they've achieved something very similar already. So it's happening. But for very simple products, they have a tool where you can go online, you can put your model in, and they'll give you a price back in a minute. So, and if you wanted one part, quite expensive. If you want it tomorrow, even more expensive. If you want 10 parts next week, relatively cheap. It's great. So this is the future of what we're seeing in these SME world. Depends on the part, doesn't it? If you've got something simple, prismatic part, you can do it very quickly. There's a lot of automated setups you can do as well. We'll put them on a block, depending. If it's somewhat more complex, which is great. Actually, with this data, you can determine, which operators are good at setting up and which are not good at setting up. I had a project once where I recorded all the data, and I realised afterwards there was one operator that took 40 minutes to use the crane and one that took 20 minutes to use the crane. And I booked it next. Guess who I'm booking? Exactly. And just a few little kind of other robotic motions. What you're seeing here, this is composites. So this is robotic weaving going on. Okay, so this is where we'll interweave carbon fibers in between each other, and you can get phenomenal shapes. You can even get big torsion tubes for shafts and things like that. That's a Titan again in the middle. Obviously, we're seeing a lot of robots for inspection. So there's this visual inspections. Quickly, inspect, and then we can put that back into our CAD systems. Robotic welding, been around for many, many years, and we see it more often. These at the bottom, these are what cobots are. This is when we have robots supporting operators next to each other. So actually, what happens if you bang into that robot? Will it damage you? Okay, most of these times they'll stop while there's been mechanisms in place. Because usually when you're operating something like this, you'll have a lot of safety guards, so you can't go anywhere near it because they're not stopping. You'll be moved, or hurt very quickly. So we do an awful lot in different space, and then communicating with each other is the biggest challenge. Different products, different softwares, different protocols. It's challenging. All right, I just wanted to put in what skills do the manufacturing engineer of the future need. So I'm.
She said, is there a lot of this occurring in the UK? You said about the Netherlands. So is this something that we're doing over here a lot as well?
Yeah. So what I would say, factories that are being created now, the new facilities have this in, these kind of technologies. But if you can imagine, 90% of factories already, they've got legacy systems. And so it's about how do we adapt the legacy systems to put this kind of technologies on to minimize disruption. The big companies, your Rolls-Royce, your McLarens, your Boeings, your Jaguar Land Rover, investing an awful lot on this. The SMEs probably need a bit more persuading, depending on what they want to be doing. And that's where we help as well within the AMRC. So, we have funding where we go in and support them for the first initial packages and stuff like that. So, yeah.
Another way to look at it though is if we're building the machines that the rest of the world are going to buy, you know, that's not a bad thing either, is it?
Yeah, so I mean, the UK machine tool, we're better at processes than we are about machine tool building. So the government are trying to reinvigorate the UK's machine tool building. So I don't know if you know, but the Northern Powerhouse Innovation Fund, they call it. So Rochdale is where they're trying to put a lot more money at the moment. There's something called AMPI, which is the Advanced Manufacturing Productivity Institute. Sounds very familiar to our name, but it's separate. And they're focusing on the machine tools themselves. And that's industry-led, not academic-led. So we are trying to reinvigorate that industry as well.
Yeah, that's worthwhile.
Yeah.
Because we're a bit off.
We're completely lagging, and even in like robotic uptake, you know, I think we're like 14th in the world or something at the moment. So we're terrible, you know, behind, you know, your Germanys, your Taiwans, and places like this. Yeah. So. Yeah. Depends on the project. So obviously, so IP is a big one. So when we do catapult projects, that's shared IP. You know, so anyone can be using that throughout the UK industry. Anyone's allowed to come and get the reports and do what they want with it. If I'm just doing a Boeing project on their own, Boeing will just own that, or Airbus, or whoever. If it's a university project, that's, for example, a PhD's done, and it's not sponsored by Boeing or whatever, the university will own it. So for me, when I did my doctorate, mine was sponsored by the AMRC actually. So then my IP actually belongs to the university and for them. And so I'm commercializing my software. I have to go to them and say, please release my IP to me so I can commercialize it without any ties. And that's what I happen to do. But it's a minefield though, because obviously a lot of these technologies build upon each other. And so you have to start having these, you know, IP logs and trade secret logs effectively to say who's got who and what can you do, and, you know, so. Yeah,
That's anti. It's growing quickly, isn't it? In the same way you get open source software.
Yeah. I think that's what the Catapult Network is trying to achieve. So, you know, the government funds the Catapult projects, and the Catapult projects are aligned with the industry roadmaps of various companies. And so they can go to these technologies that we've been developing, you know, through our centers, any of the partners can then use. And so, you know, so if there's these kind of what you call broad generic projects, anyone can get them. That's the whole point of them. And it's quite a lot of funding. You know, for us, it's about a third of our funding is from that one single pot. So I included this because I'm the undergraduate admissions tutor for my department for recruitment. So, you know, when I'm recruiting people in our field, which control engineering is mine, it's changed an awful lot. When you think about a manufacturing engineer, I'm sure most of you think about, you know, an old man in a blue jacket, you know, running up and down a factory. Okay, so that's what it was, and so there's many ways. But actually, I think my presentation today has shown you that, you know, you need to have automation, robotics, and mechatronics. And the IET, the Institute of Engineering and Technology, and the IMechE, Institute of Mechanical Engineers, the report they brought out last year stated this is the number one thing they want students to have and graduates to have, you know, on the top line. And you need to have these skills, you know, AI, sustainable manufacturing has to be number one, life cycle analysis, material science. Material science is ginormous and fascinating. Digital manufacturing, control, data science, coding, but really, you know, these really good communication skills and design thinking and creativity as well. You know, so soft skills are ginormous, and we do a lot of that in our, you know, in university.
When you say university, yeah, so we feel moving so quick, business roles.
Yeah. Yeah, it is. But then it is going incredibly fast, especially now when you think about generative AI and what's happening. But there are still a set of fundamentals, a set of skills that you can have, you know, and it's about how do I take a system and how do I model that system and then figure out what tools I can apply to it. You know, what are the limitations of each tool, what's the most appropriate tool to use. That's kind of things that we're looking at really with them. Yeah. But you're right, I mean, it's a nightmare. So what I do every year is my MSc students, you know, I have about 5 or 6 every year. and I set them a different machine learning method, each one of them. And so by the end of the summer, they taught me 6 new methods. And so, what's next? And I put this into ChatGPT as well. Say, well, where are we going? So, Industry 4 and smart manufacturing are here. 3D printing is absolutely everywhere, and it's the future for a lot of this stuff. You know, advanced robotics and automation is key. Digital twins and simulation. So we've covered that. So that's great. So I was on the right lines. Sustainable and green manufacturing, supply chains, AI, and then this mass customization. You know, you might have seen these, you know, these documentaries on TV where you go to the Bentley factory and every car that comes out is, you know, customized with this perfect, you know, different kind of leather and different kind of. This is what it's going to be. You know, you're going to go online, you're going to order a car, not a Bentley, right? But it's going to be customized and built, you know, through digital twins and through all these technologies, you know, easily, not more expensive, cheaply. This is where we're going. So it didn't say anything about Industry 5 on there, but then I asked it when it was kind of when the training information went up to. ChatGPT said to me that information is only good enough for January 2022. Please remember, if you're creating models, it's only as good as the data that you give it. Okay. So obviously with this, it's not going to tell me anything. So for me, this is what's next. Industry 5. It's about linking humans, sustainable manufacturing, resilience in systems, with artificial intelligence and everything working together. So how can we create these ecosystems and this extends past the manufacturing world, I would say. You're going to see this within the medical sector. You're going to see this in the pharma world. Okay, you're going to see this in your home, everything connected. But it's about how do we have these trustworthy systems that are all linked, you know, with AI working together, and it's going to put the human at the center of it. You know, so we're not going to be in a world where robots are going to replace humans. It's going to be a world where they work together in a very safe way. Thank you. Oh, yeah.
Online questions as well. Just back on the side. But yeah, just far away.
Yeah, so the question is, do we interact with local schools in Sheffield? Yeah, absolutely we do. Yeah, so no, we do an awful lot of work with schools. So the AMRC, we've got our own STEM program, and we're working schools all over. Personally, as well, for me, as part of my undergraduate role, you know, I spend a lot of my work trying to develop, trying to get more women into engineering. So, for example, I've got an event this year called Women in Control, which is aimed at 15 and 16-year-old girls. So it's when they can make their decisions to do A-level maths early, and things like that. So yeah, we do an awful lot of work, and we host them both at the AMRC, and I've got my own robotics labs in the university we host, and we do a lot. But if there's any schools that you want us to go and talk to, send me an email, and I'd happily kind of arrange something as well. So. Yes. Yeah. The question was about, you know, how do we get research into the real world ultimately, or, you know, people in the real world understand what's going on in academia? A couple of different ways. So one of my jobs, so I'm the impact and innovation lead. My department, I speak with, you know, I work with my colleagues to either commercialize or license their software or their research. Give you an example. So I developed some software that can predict cycle times. You know, for me, I then applied that to a Rolls-Royce plant, okay, the ANSTI plant. I was able to be able to predict, okay, the behavior of the machine tool. It was an old machine tool, like 20 years old, with high accuracy. We then that supported our rollout of the new products, and all of a sudden that's a case study now. Now, because I've got that tick in the box, now Boeing are interested, now other ones are interested, and we're going down that licensing route to get that out. So that'll be out there. Yeah.
Any more small companies who just don't seem to know how to access this information?
Yeah.
At the university, an individual who
a really good idea, but I need to.
Yeah. So there's things called the knowledge exchange networks and knowledge transfer networks. And so small companies that can access the university through what we call the KE schemes, and there's funding to be able to do that as well. There's also the Made Smarter program, which is ran for businesses, so they can access pots of funding. They can even get placements where they can do. They can get a grad, for example, to come and sit within the company, and then support that knowledge exchange and that knowledge transfer across. So there are mechanisms. I think for most small businesses, SMEs, they're quite engaged with the Made Smarter networks, and there's quite a thriving network of which they can access. But yeah.
Question, work in the alternative broking space, so fermentation.
Okay.
When you have your what next, like that, could be
Yeah.
generation. Still facing significant challenges getting past. Just wondering, based on your experience in other sectors, seeing that jumping period, where do you see operating?
Good question. Yes, I think the question was about in different industries, how can we, address that valley of death, and how can we get products from research into industry? I would say that's the whole point of the Catapult network. And so, I'm part of the high value manufacturing, but there are 7 other networks that are there, and I think, yeah, exactly. So, engage with the catapults, the right one, and there's different schemes as well that you can support, and there's funding available, especially for SMEs too, as well, through the catapults and things like that. So, yeah.
Any more questions? What's your view of your friends in marketing that just pretend smart?
Yeah.
CES show, guess what? Released last week. An AI killer. It makes you sleep better.
Yeah. It's everywhere, and I know. So I've been part of some startups as well, and I was part of one. And then, within 6 months, all of a sudden, it was an AI startup. It hadn't seen an AI in its life. But all of a sudden, it's a buzzword, and so you can get funding for it, and you can do things. And a lot of this stuff's been out for many, many years. A system that learns, that's not novel. You don't need AI necessarily to do it. There's other different things to do it as well. Yeah.
But the public see this, right? They see it in the advert. Well, it's an AI washing machine.
Yeah.
So I guess I'm an engineer.
Yeah, and do you need an AI washing machine? You don't need to have AI on everything. And actually, if we look at the sustainable world, we want to have minimum computation, minimum power. Because it has to go somewhere. This data is going to go to some cloud storage center somewhere, probably off grid. Where cheap energy is happening, and actually, it's unsustainable because that has to power that somewhere. So at some point, we have to think about the sustainability of data, the cost of it to the world.
The people that are involved in quantum physics, thinking the buzzwords now moving on to like that.
Yeah. Yeah, exactly.
Quantum pillows. No.
Yeah.
It's good.
Yeah. That's funny. Hiya.
Very beginning, you said your one of the main things was net zero.
Yes.
And I understand, as we have professor engineering attributes in customized cars, was it? How does this apply to the situations which are poorly for the planet? How does this apply to the textile industry, which is incredibly damaging with water waste and fashion and all the rest of it? I can understand it. It's brilliant. Can it jump over to these other concerns?
Yeah.
I don't know, but I'm much more concerned about the damage done by the textile industry, about whether a Range Rover is going to have the right V length.
Yeah. So the question was about if these technologies go to the textile.
How they transfer.
Yeah. I'm not sure, I'll be honest, because it's not my domain for the textile industries. What I will say is, things like the foundation industries and, extracting these materials, from source, I might do some work to make machining these a bit more efficient. I might make the whole process, of its net zero life. But actually, 90% of the energy is getting the metal out of the ground or converting it into some, sell it for me.
You know what's going on with the out of the ground.
Yeah.
We know what's going on with the textile industry, the amount of water that
Yeah.
moves. And I just wonder, is there a transfer between?
I imagine there's a lot of technology that can go across, but I can't give you an answer. I'm not sure. I think one of the things that we're seeing now is carbon accounting. That's what you're going to see now. So when you go and buy a product, or you place an order, no longer will it just be on cost. The decisions that your business will make will be on the carbon accounting, and the technologies that you're seeing here will be able to give you more accurate carbon accounting details. I think that's the future stuff. Okay.
Any more questions? Well, if not, let's put it together, please.
Thank you, everyone.